is being recorded. Okay, I can continue.
Okay, welcome everyone to the afternoon session. It's my honor to introduce our first speaker, sorry, from the University of Warsaw, and he's going to tell us about geometric ellipticity. Please.
So first of all, I'd like to express my gratitude to the organizers for inviting me here and for organizing this, undertaking this challenge. So thanks. Okay. So about geometric ellipticity, first of all, I need to define what I mean. So I'm dealing with geometric variational problems, and by that I mean problems which look like that. We have a functional defined geometric object, and we want to study its critical points. This is the most general statement of the problem. One example is the plateau problem, where the set of geometric objects would be, say, C1 manifolds with fixed boundary, or currents with fixed boundary. Or the second example is an isoperimetric problem, where the set of competitors, set of geometric objects would be, say, boundaries of all open sets with volume 1. So you see, it fits, at least these two problems fit in this setting. But in my talk, I will focus on more specific problems, namely, so now I'm going to define the problem that I'm dealing with. So we are given an open set U in Rn, and F is a map from the Grassmannian, G and K is Grassmannian of K-dimensional subspaces of Rn, and it maps this Grassmannian into some interval, so it's bounded away from 0 and bounded away from infinity. I will always assume it's continuous, but even maybe smooth, as good as you like. So we are given this functional, this integrand, and now we want to define geometric objects that we want to consider. So for me, the geometric objects will consist of variables, and variables by definition are random measures over this Cartesian product of U times the Grassmannian. So any random measure on this Cartesian product is a variable. So now we define the functional. The functional I want to deal with is defined by variables, and it acts on a variable simply by integration of f, which is a given integral. So usually f is allowed to also depend on x on the point of the open set U, but for simplicity and for purposes of this talk, I will only talk about this kind of functional. And to make it maybe less abstract, if you think about variables, they are random measures that you should have in mind very particular variables, namely those that are associated to some set M. Say M is a C1 manifold or an HK rectifiable set, and a set for which you can define a tangent plane. So with such a set, we associate a variable, VKM, and it's a random measure over the product. So I have to say how it acts on subsets of this product. So I say, okay, it measures the set of dollars where this is in the A. So basically, it chooses at each point, it's supported in M, and it chooses at each point in the Grassmannian part the tangent. So this is, if you don't know what are variables, you should think that they are these kind of things. So in particular, C1 manifolds are all C1 manifolds, say, submanifolds of the open set U lie in the space of variables by this association. Okay, so I introduce some notation. Double bar, V double bar is a measure now defined over U, not over U times the Grassmannian, and it's just the projection of the variable onto the first coordinate. And I also introduce the symbol VF, which is V weighted with F. Just for brevity of the notation, it will be useful to use this. And now the first variation. Because I said at the beginning that we want to study critical points of this functional, so we have to define what it means to be a critical point, and for that I have to define the first variation. So I use this symbol delta FV, which is the first F variation of V. Its type is a linear map on vector fields. G is supposed to be a compactly supported in U smooth vector field. And once you give me a vector field, I have to say how the first variation acts on this vector field. So first, you take the flow of this vector field. I call it HT. You push forward the variable with HT, and you compute its energy, and you differentiate at 0. So of course, I didn't define this is push forward and so on, but I think for the purposes of this talk, I don't need all these formulas. The only formula I need is this one. So the first variation can be expressed by integrating this red thing. So we have to understand what is this. So dg is just a derivative, which is a linear map of Saturn modes, and is composed with another linear map, and we take the trace. And the other linear map, which plays a crucial role in all this theory, is PFT. And well, it's a projection. This thing means it's a projection. And the image of PFT is T, which means it's a projection onto T, but it's not orthogonal unless the derivative of F is 0. So it's an orthogonal projection if and only if the derivative of F is 0, which means it's an area integrand. It means that F is constant, well, if it's 0 on all T, then F is just constant, and then we call it constant F an area integrand. Because then, here, if you look at this integral, this would be just the area of your variable, the mass of your variable. And since this PF is a projection onto T, I think it's good to call it an F divergence. It's some kind of a divergence of this vector field T. Okay, so just from this side, you have to remember maybe this one formula. Okay, so yeah, so the main obstacle in doing regularity theory for this kind of critical points for F-stationary variables is that we don't know whether they are alphas regular. And the typical way of obtaining alphas regularity for a variable is to prove the monotonicity formula. And unfortunately, monotonicity formula only works for the area integrand. And to understand that, let's see how the proof goes. I will not give you the proof. I will just wave my hands a bit. So assume you have a stationary variable set, and you have a ball inside your open set. You test your bifold with the following vector field. G of x is x minus a multiplied by a cutoff function. The graph of the cutoff function is here. So it's 1 up to r, and then it goes to 0. And when you test the variable with this function, you compute the first variation, you pass the limit of epsilon, and you get the following formula. So on the left-hand side, you get the density ratio, derivative of the density ratio, and on the right-hand side, you get something, the derivative of this. And assume now that all F-stationary variables have monotone density ratios, which means the left-hand side is non-negative. So assume the left-hand side is non-negative for all variables which have, for all F-stationary variables. And then you can work, and end up with the conclusion that the integrand on the right-hand side must be non-negative for all Tn. And once you end up with this conclusion, it's a very simple exercise in linear algebra to say, well, if you have a projection which is positive definite or non-negative definite, then it must be such a joint, which means it's an orthogonal projection. And once you know this is an orthogonal projection, identity minus PF. So then you, if you recall the previous slide, you will end up with knowing that this must be constant, F must be constant, so this is an area. You can find this result in the paper of Alan from 1974. And even more general, maybe you wonder, you can change the norm, change the balls here, I don't know. Well, Alan is saying no, you cannot do anything. So, so this is the main obstacle for doing regularity, that for any integrand that is not area, you don't have non-density. Maybe you have also regularity by some other means, but not in this way.
Okay, so I will just a few comments for this slide. First of all, I was claiming that this implication holds if this is non-negative, then for all v which are f stationary, then this integrand must be non-negative. Okay, to be honest, I never checked that this is true. So, but it seems plausible. Anyway, so what Allard does is proving the following theorem. Okay, he has this sigma, which is basically this sigma in our situation is basically this integrand, this expression, and he's saying that in dimension bigger than 1, this sigma is non-negative if and only if there is a linear change of our coordinates in Rn, which transfers the integrand phi, which is in the energy, to a constant times the area integrand, and transforms the metric rho to Euclidean metric mu. So rho is something that he's using, well, he's proving a more general result. I have only balls, Euclidean balls here. He's also proving that you have a similar formula if you take non-Euclidean balls with respect to some norm rho, and you have something on the right hand side which he calls sigma, and if this is non-negative, then you have this theorem. So rho must be Euclidean, phi must be the area. So what I proved here is a lot simpler. I mean, this integrand only for the Euclidean balls. You have this integrand, and this is a small exercise to see that this integrand can be non-negative if and only if this projection is an orthogonal projection. Okay. This is it.
Okay, so now for a second, but anyway, we want to kind of study these functionals and critical points, and we want to maybe find some conditions on the integrand f that would allow to say at least something about the something meaningful about the critical points. So let me just briefly describe what happens with minimizers. So assume we have a family of closed subsets of U with finite measure, and this family is closed under deformations, Lipschitz deformations, and here this condition says that this deformation moves point inside U, but not near the boundary of U, basically. We are allowed to deform the set inside U, and you don't go out of the family, and then there exists a minimizer. So the first condition, the first item says it's a minimizer, so it's the energy of the variable is less than energy of any member of the family, and it's actually a limit of variables. When I say limit of variables, I always mean weak limit of measures. And then you can derive that the support of this part of the variable that lies in your space in the set U is HKK rectifiable. And you can also derive that these two measures, if you restrict HK to the support of V and the weight member of V, they're mutually absolutely continuous and also singular away from the boundary. So these are all of that you can derive without any further assumptions on F. But there is something missing because we would like sigma to be a minimizer, and we don't know that yet. Because only if F is elliptic then you have this condition that your bifold always chooses the tangent plane in the Grassmannian part. And then you can conclude that you have this equality, because otherwise you wouldn't. So, and then sigma is really minimize that. So I'm stating here some results, some existence results, and maybe it's not very precise, but because in different flavors, this result were proven by different people, like Sam from Eiffelberg and Alben, and last year's with the Finnish and Tony Garosa, Skrigadin, wrote a series of papers, which some of them were called the Camilo de Reis and just magic. I have a paper with French and Fine about this, and there's also some papers by Harrison and Pew. Gita Rittel is also should be mentioned among these people. So this is what developed here. But what I want to emphasize here is that ellipticity gives this condition. Ellipticity is something that should give this condition. And now I will describe what means elliptic. So I will start with Alben's definition, the original Alben's definition of ellipticity. First, we'll define what is a test pair. A test pair consists of two sets, S and D, where D is a flat K-disk, it means that it's a disk inside a K-plane, and S should be an HKK rectifiable and compact, and the final condition is that, well, the boundary of D, which is a K-minus one-dimensional sphere, should be in S and cannot be a retroact of S. This is Alben's definition. Actually, Alben didn't define test pairs, but okay, I'm giving you the essence. So the definition of being elliptic is here. So whenever you have a test pair, the energy of S should be bigger, not less than energy of D. Which means basically that if you have a flat K-disk, if you want to solve the plateau problem, say with the boundary of D, then D should be minimized. That's basically what it means. And there is also a quantitative version of that, a uniform Alben elliptic. F is called uniform Alben elliptic, abbreviated UAE. If there is a constant such that you have a quantitative control of this difference. Not only if S is bigger than phi of T, but also you can compare it with the area. So this is the basic original Alben's definition, and it has many useful properties. So if you look in this paper of Alben, okay, I mentioned here two papers. So he's at least claiming that these properties hold. Some of them have proofs even. So a C2 neighborhood of the area integrand is uniformly Alben elliptic. So this class is non-trivial set. It contains something. So if you push forward by a diffeomorphism, then you push forward an integrand by a diffeomorphism, you're still uniformly Alben elliptic. And the set of all uniformly Alben elliptic integrands is a convex set in the space of all functions from the Grassmannian to reals. And also, you can find in codimension 1, there is a full characterizations of uniformly Alben elliptic integrands, and these are supposed to come from uniform convex norms. And by that I mean if you're in codimension 1, it means the F is defined on hyperplanes, and each hyperplane has a unit normal vector. So this gives you a correspondence between the norm. So you assign to this hyperplane the norm of the unit normal vector. So this is what I mean by F comes from the uniform convex norm. So we know that, but still there are questions. Are there any non-trivial elliptic integrals? So what I mean by non-trivial? I mean they don't fall into these categories. So they are not close to area, it's not a push forward of the area. And so for example, one example is that we don't know whether it's elliptic or not in the sense of Alben is this Bussmann-Hausdorff integrand, which is written here. And so if you take a non-Euclidean norm on Rn, and you can produce out of it a metric, and from this metric you can produce a Hausdorff measure, and this is some kind of anisotropic Hausdorff measure. And then you can express it in this way. I mean, this Hausdorff measure can be expressed as this energy, with F being given by this formula here. And this formula is called the Bussmann-Hausdorff integrand. There are other options as well, and I think no one knows whether they are elliptic in the sense of Alpen. So another question is there some kind of convexity sufficient for ellipticity? This is also something that we don't know. In comparison, for example, to PDEs, where convexity of the functional of the integrand usually gives some kind of quasi-convexity. Here, you don't know. And if someone gives me a functional or an integrand given by a specific formula, just write down a formula and please now someone asked me to check whether it is elliptic. I don't know how to do that. So we would like to have some conditions which actually allow to check that some integrands are elliptic. This on top of this slide you have the property that were desired for the minimizer that was missing. If you don't assume anything on F, then this property was missing. So ellipticity should be something that ensures that this property holds, right? So back in 2016, November 2016, we met with Ulrich and with Ulrich Manner and Antonio de Rosa online, even though it was not yet COVID time. And we were discussing my result with Yanqing Fang and what was needed to have it in the end, and maybe ambient ellipticity was not the right. And we invented this condition BC. It was called BC because it was a box condition, because there was a box on the blackboard. And we invented this condition and we said, yeah, okay, and we agreed that this is enough, that the result of Yanqing Fang, mine and with Yanqing Fang, would work also if we assume only this. So what does it mean? F satisfies this condition BC if for all variables of this structure, so HK restricted to some K plane times some probability measure on the Grassmannian. If for all variables of this structure, if they are F stationary, then mu has to choose the right plane. Right? So this is basically what, well, this style, I mean, we wanted to have this property which is written in the top, and we invented this condition. And then Antonio said, oh, but we have this condition AC, the one, which was earlier invented by Guido De Filipis, Antonio De Rosa, and Francesco Guidin in an earlier paper. And so, yeah, so we invented BC, and there was AC earlier, right? And we wanted to compare these two things. So first of all, we need to maybe first understand what AC says. So let me read it. So F satisfies the atomic condition, abbreviated AC, if and only if, for any probability measure on the Grassmannian, if we define AF mu by this formula, PF comes from this first variation, right? Then two conditions hold. If always for any probability measure, the kernel of this AF mu has to be at most n minus k. N minus k dimensional, and if it is exactly n minus k dimensional, then mu has to choose the right plane. Well, actually, for some plane, this is not written exactly. There exists T for which mu is a Dirac on T. So this condition was introduced in this paper by, it's mentioned on the slide. and they look kind of similar because the conclusion is always mu equals Dirac T, and upstairs it's also this. And if you look inside the definitions, reveal all the details, then you will see that they are the same. BC and AC are the same. So our theorem with Antonia, we proved that BC and AC are the same. It's not a circular lemma. It's really simple if you just read all the definitions and understand what they say. But the most significant part is that AC implies AE. So any integral satisfying the atomic condition satisfies also underlying BC. So I will give you a sketch of the proof very briefly. So it goes by contradiction. Assume we have an integrand which is in AC but not in AE. Tilde is a subterranean difference. So if you recall the definition of AE, it means that you can find a test pair for which you have this inequality. So the energy of S is less than energy of D. So we can actually assume S minimizes here. Actually, for that, we need this result which I haven't mentioned, but proven for BC, for not underlying, but for integrals satisfying BC. So we also in this paper proved that we can do that. So we find a minimizer of in this class of S tilde, where S tilde D is a test pair. So D is fixed, and we take all surfaces that together with D create a test pair. So if you don't remember, S tilde cannot be retracted onto the boundary of D. This is the main feature. Okay, so since the energy of S is less than energy of D, we can find a number theta which is strictly larger than 1. This is important, strictly larger than 1. It's the ratio of the measure of S to measure of D. Well, this is basically because well, the area integrand, if phi of S is strictly less than phi of D, so S is not D, there's some significant difference between S and D, and area is of course minimized by the disk. So this has to be strictly larger than 1. Okay, now we produce a sequence by tiling D with scaled copies of S, and this is the part I want to write. I have to draw.
Okay, one more thing, addendum. If you don't see it on the video, but what I was drawing on the blackboard was the following: the tiling. So you have a test pair S and D, but now assume D is a cube. Okay, cube, and then you have a surface which looks like, I don't know, something like that. And what you do, this is S, I mean S is here, D is downstairs, and then you construct R1 by scaling this down and taking many copies of the same surface scaled. So this is S, 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 and S, and you have like 2 to the k copies of S here, and then you proceed. You do the following, this tiling once more in each. You do it more and more and more, and you end up in the end with a flat disk, which is using this homogenization procedure gives you, say, R infinity, which is the support, well, actually I call it sigma, of the limit variable. Okay, so that this is the tiling procedure that is not visible in the video.
So Okay, so imagine first that D is not actually a disk, but a cube. So you have a D here, and you have a surface somewhere attached to it. Some surface S. And what we do, we take we divide it into 2 to the k. So this is in our k. Okay. Which is in k dimensional. So we divide this cube into 2 to the k each, and we put a copy of S in every and we just, we do this. So we have 2 to the k copies of the surface. And this is R1. So we do that infinitely many times. We produce a sequence like that of some things. And then we pass to the limit, to the variable limit. And you can it's easy measure theory to show that the limit is of this type. So it has to be of this type because when you scale down, S is compact by definition. So if you scale down, it's flatter and flatter, so it's supported in P in the limit. And then because there is some homogenization going on, so it's translation invariant, so it must be the Lebesgue measure of T, basically. And then you have mu here, and mu does not depend on the part x because of the homogenization. It's also translation invariant. So we get a variable of this type, and then we also have to observe that if you look at this distribution of elements here, it's the same as P. Because if you choose one element and you have as many points with this element here, right? So we have this like each element of our sequence has the same energy as S. So now we conclude, but S was a minimizer, so it must be a critical point. So the first F variation must be 0. Hence, because F satisfies PC, which is the same as AC, where is the Dirac delta? And then we have this contradictory estimate. Okay, phi FD is less than theta times phi FD because theta is strictly greater than 1. Then it is equal to this equality here is because mu equals Dirac on T. So you can actually, if you plug in the definition of V, it will be equality. Here, this equality is because phi F is actually continuous with respect to weak convergence of variables. So we have this equality here. Then, then because for each I the energies agree, then actually this is a constant sequence. So it's phi of S, and that's less than phi of D. But it's a contradiction because phi of S was supposed to be less than phi of D. So it cannot happen. There is one tricky part here, namely. We know that S minimizes phi F, and we produce this sequence of RIs. And why should RI be a test pair? I mean, the condition is it cannot be attracted from this boundary, right? So this couldn't be attracted, but you see, when you do this abstraction, you modify abstraction. So there is a very kind of, and we know we have to know that Ri is a test pair because otherwise we don't know that phi of Ri is a minimizer. Yeah, and we don't know that the first variation is 0. So we need to know that Ri is actually in the class A. But to prove that, there is involved algebraic something that involves tools from algebraic topology, and I challenge you to read it. I would like to talk about something else in the remainder of my talk, so I will leave you with that. as it is. Okay, so now I want to talk about the condition AC. So first of all, we denote Z by calligraphic Z, this space of linear maps from Rn to Rn, and it has a Euclidean structure where the scalar product denoted by bullet is given by this formula. So I guess this is called also the Hilbert-Schmidt product, but anyway, I just want to treat this space Z as Euclidean, as a Euclidean space. So if you recall the definition AC, there was something about kernel of this AF mu. So assume this is bigger than n minus k. So this contradicts. So this assumption about the kernel of AF mu actually contradicts AC. So assume mu F does not satisfy AC. And then, so assume there is some mu for which kernel of mu is greater than n minus k. Then you can find something n minus k dimensional in the kernel, call it T-perp, and T will be the orthogonal space. And assume further that there exists QF T, a linear map such that the following two conditions hold. First of all, T is in the kernel of this linear map, and the scalar product of these two maps for each S, the scalar product with PFS adjoint of PFS is non-negative. Then I claim that the atomic condition must be satisfied for you. Why? First of all, it's simply linear algebra to see that the image of the adjoint of QFT is T-perp. Simple. Then it follows that since the image of QFT star is T-perp and T-perp is the kernel of AF mu, then this map here is 0, so the trace is 0. So in the end, we get 0 equals this product. And since scalar product is linear, we can put it under the integral, and we have this formula. But condition number 2 now says that the integrand in this formula is non-negative, which means that for mu almost all S equals T, which means that mu is a Dirac in T. Right? And consequently, AF mu is just equal to PFT star, and the dimension of the kernel equals n minus k. So whenever you have, we started with this assumption that it's greater or equal to n minus k, and we ended up with this. So the atomic condition, at least for this mu, holds. If you look at condition number 2, what does it say geometrically? What does it say? So first define calligraphic G. Calligraphic G is just the image of the Grassmannian under this map PF star. Right? And condition 2 says that G, as a subset of this calligraphic Z, which is a Euclidean space, lies entirely on one side of the hyperplane span QF, orthogonal to QFT, and touches this hyperplane at one point. So it's convexity, right? It means that for each T, one can find, so this is a definition. If you have a geometric object and you can touch it at one point from all directions, at each point you can touch it with a hyperplane, then we can say it's a strictly convex set. It's a reasonable definition. Actually, okay. I think there is a developed theory about convex hypersurfaces, which are supposed to be boundaries of convex sets. But maybe I didn't do much research on that, but I don't know much about, is there any research on higher codimensional convex sets? Maybe you know. If you know, just tell me. But it's perfectly reasonable to say that G is strictly convex under condition, and if this holds. So there is a paper by Antonio De Rosa and Riccardo Tione from a few months ago in archive. They introduced this scalar atomic condition, and they say, okay, choose QFT to be exactly this map. they use this formula, where f bar is defined this way. Okay, so they use this formula, and my suggestion is to, I wanted to use another, I had another candidate for QFT, but yesterday I just computed the same. So the J formula is equal to that. So if you think about this, what is this? If say this P FT, this is P, this is P FT, so it's a projection along this direction. So identity minus is just a projection of T onto this space, and this space I would call F1. So kind of normal projection onto the normal space. And yeah, so they introduced this scalar atomic condition, which is basically assuming that that condition 2 holds with this choice of QFT. And once you assume condition 2 holds with this, okay. So there's one remark here to check it. It looks like it's now it's checkable, right? But still, in their paper, they given precise, specific integrand given by a formula, and they try to check it. I don't know whether they succeeded in the end, because I checked on archive a few days ago and there is nothing. I mean, no change since December last year. And in the paper, they check only half of not. They give a formula for certain integrand, and they check. I don't know whether Antonio is listening, but anyway, maybe if you can tell, I don't know whether he is there, but I think they didn't check the full stack. Because you have to choose 2 points and you can S and T independently, and it's like proving, well, it's a bit difficult computationally, right? So they also in their paper they also have a uniform version of the stack, and they say, okay, you have quantitative control of this scalar product, which would correspond to some uniform convexity, which means that, well, basically it means that you control, you have this strength set coming out of G, which is a point here, you have this hyperplane, here you have Q, right? So you control how fast it transbends, right? Quantitatively. So the uniform, so it's like a uniform convexity condition. So with this uniform stack, they prove that for Lipschitz graphs that they are fully regular, and they proved a very important feature, the Cauchy-Pauli inequality. So but here they, of course, assume a priori that we are dealing with Lipschitz graphs. So it's not, you get alpha regularity for those things a priori, right? So assume a priori they are alpha regular. So now I want to spend the last 1 minute saying about my ongoing project with my student, Mariusz Janos, who is doing his master thesis with me, and possibly maybe would like to continue doing some other research. So we should define Ft to be this product, scalar product, where QFT is equal to that. Then you can easily check that this picture that I draw here actually true, means that this is the tangent plane, which is G, is contained in this hyperplane, which is orthogonal to QFT. So it's. So I should finish, right? because my timer, I have still 5 minutes. Okay, great. So it seems plausible that some kind of second derivative, positive definiteness of second derivative of this map ft should be enough to prove uniform convexity of this calligraphic G. But this we have to check, and another thing that we're working on is that, well, maybe strict convexity of G is necessary. I mean, we know it's sufficient, but I would say it should be necessary as well for AC to hold. Okay, so this is all. Thank you for listening.
Any questions on this level?
In the definition of the test set, could you imagine, let's say, smaller class of test sets, but would give you the same result as the ellipticity and which would be simpler to test?
Well,
like, the images of the disk.
right, yeah, images. That would be, yeah, that's a good question. I don't know. So if not, okay, so I can repeat the question. So the question is whether I can imagine a different set of test pairs, not so general. Maybe a smaller set of test pairs would be enough. So the question is enough for what exactly? So for, I guess, because I'm going to introduce this for proving actually regularity of minimizers. So he's and I'm not, I never read it very thoroughly, the regularity part of his paper. So I'm not so sure whether that would be enough if you only consider this, like images of disks. So, well, basically my answer is I don't know. But certainly for currents, for example, if you that's even a larger concept. If you consider here only S and D, which have a structural current, and the current boundary of S would be boundary of D, then it's a classical result of, I don't know who, but Federer in his book certainly proves it's a like 5-line proof that convex integrants gives you ellipticity. That's easy, right? For currents, yeah. But if you allow more general sets like here in this definition, then no. We have to work.
Any other questions? Okay, now let's thank the speaker again.